Over the centuries, engineers and architects have devised ever new ways to build taller, stronger and more beautiful creations using game-changing materials like steel girders, earthquake-proof foundations and glass curtain walls. But what does the future hold for construction technology? Will there come a day when noisy construction crews are replaced by swarms of autonomous nanobots? Will the cracks in concrete foundations one day miraculously heal themselves, or gas stations be replaced by electric cars running on self-charging roads? Keep watching for our full list of 10 of the most exciting construction innovations of the near future. Self-healing concrete. Concrete is the single most widely used construction material in the world. In fact, it is the second most consumed substance on Earth, after water. Think of all the concrete homes, office buildings, churches and bridges built each year. Concrete is cheap and widely adaptable, but it's also susceptible to cracking and deterioration under stresses like extreme heat and cold. In the past, the only way to fix cracked concrete was to patch it, reinforce it, or knock it down and start from scratch. But not anymore. In 2010, a graduate student and chemical engineering professor at the University of Rhode Island created a new type of smart concrete that heals its own cracks. The concrete mix is embedded with tiny capsules of sodium silicate. When a crack forms, the capsules rupture and release a gel-like healing agent that hardens to fill the void. This is not the only method of self-healing concrete. Other researchers have used bacteria or embedded glass capillaries or polymer microcapsules to achieve similar results. However, the Rhode Island researchers believe their method is the most cost-effective. Prolonging the life of concrete could have huge environmental benefits. Worldwide concrete production currently accounts for 5% of global carbon dioxide emissions. Smart concrete would not only make our structures safer, but also cut back on greenhouse gases. Carbon nanotubes. A nanometer is 1/1,000th of a meter. That's impossibly small. A single sheet of paper is 100,000 nanometers. Your fingernail grows approximately 1 nanometer every second. Even a strand of your DNA is 2.5 nanometers wide. To construct materials at the nanoscale would seem impossible, but using cutting-edge techniques like electron beam lithography, scientists and engineers have successfully created tubes of carbon with walls that are only 1 nanometer thick. When a larger particle is divided into increasingly smaller parts, the proportion of its surface area to its mass increases. These carbon nanotubes have the highest strength-to-weight ratio of any material on Earth and can be stretched 1,000,000 times longer than their thickness. Carbon nanotubes are so light and strong that they can be embedded into other building materials like metals, concrete, wood and glass to add density and tensile strength. Engineers are even experimenting with nanoscale sensors that can monitor stresses inside building materials and identify potential fractures or cracks before they occur. Transparent aluminum. For decades, chemical engineers have dreamed of a material that combines the strength and durability of metal with the crystal-clear purity of glass. Such a clear metal could be used to construct towering glass-walled skyscrapers that require less internal support. Secure military buildings could install thin transparent metal windows impervious to the highest caliber artillery fire. And think of the monstrous aquarium you could build with this stuff. Back in the 1980s, scientists began experimenting with a novel type of ceramic made from a powdery mix of aluminum, oxygen and nitrogen. A ceramic is any hard, usually crystalline material that's made by a process of heating and cooling. In this case, the aluminum powder is placed under immense pressure, heated for days at 2000 degrees Celsius and finally polished to produce a perfectly clear, glass-like material with the strength of aluminum, known as transparent aluminum, or ALAN. The space-age material is already being used by the military for making armored windows and optical lenses. Permeable concrete. During a heavy storm, sheets of rainwater pour down on roadways, sidewalks and parking lots. scouring up surface debris and pollutants and washing potentially toxic chemicals like gasoline directly into sewers and streams. The U.S. Environmental Protection Agency identifies stormwater runoff in paved urban areas as a major source of water pollution. Nature has its own way of filtering out toxins from rainwater. Soil is a magnificent filter for metals and other inorganic materials. As rainwater passes down through soil levels, microorganisms and plant roots absorb excess chemicals. Knowing this, engineers have created a new type of permeable concrete that allows rainwater to pass right through pavement and let nature do its work. Permeable or pervious concrete is made with larger grains of rock and sand, leaving between 15 and 35% of open space in the pavement. Slabs of permeable concrete are laid atop gravel or another porous base material that lets rainwater settle to the soil substrate beneath. Permeable concrete is an excellent replacement for asphalt in parking lots. Not only does it significantly decrease runoff, but also the lighter color of concrete reflects sunlight and stays cooler in the summer. Aerogel insulation. If Michelangelo's famous marble statue of David was made of aerogel, it would weigh only 2 kilograms. Aerogel is one of the least dense substances on Earth, a foam-like solid material that holds its shape despite being almost as light as air. Some types have densities just 3 times heavier than air, but typically aerogels are 15 times heavier than air. You might think of gel as a wet substance, such as hair gel, but aerogel is made by removing the liquid from the gel. All that's left is the silica structure, which is 90 to 99% air. Aerogel is almost weightless, but can be spun out into thin sheets of aerogel fabric. In construction projects, aerogel fabric demonstrates super-insulating properties. Its porous structure makes it difficult for heat to pass through. In tests, aerogel fabric had 2 to 4 times the insulating power of traditional fiberglass or foam insulation. Once the price comes down, it could be widely used in construction. Temperature-reactive tiles. If you were alive in 1991 and lived above ground, odds are good that you owned a Hypercolor t-shirt. By some scientific miracle, a miracle called thermochromic dye, the folks at Hypercolor made t-shirts that changed color with your body temperature. The commercials made it look super cool, but in reality the hottest parts of your body are usually your armpits. Glowing armpits are not super cool, right? Today, a company called Moving Color manufactures glass decorative tiles coated with thermochromic paint that come alive with changing surface temperatures. At room temperature, the tiles are a glossy black. But when you touch the tiles, or hit them with direct light or warm water, the colors transform like the northern lights into iridescent blues, pinks and greens. The coolest application has to be the color shifting shower. The good news for Moving Color is that houses don't have armpits. Robot swarm construction. One of nature's most ingenious builders is the humble termite. With a brain the size of a grain of sand, it works alongside hundreds of thousands of mound mates to build colossal and complex mud structures. Termites captured the attention of Harvard robotics researchers because the insects don't take orders from some central termite architect. Each termite works alone according to genetically programmed rules of behavior. Together, as a swarm of single-minded individuals, they create monumental works of mud. Inspired by termites, researchers at Harvard's Self-Organizing Systems Research Group have built small construction robotics programmed to work together as a swarm. The 4-wheeled robots can build brick-like walls by lifting each brick, climbing the wall and laying the brick in an open spot. They have sensors to detect the presence of other robots and rules for getting out of each other's way. Like termites, no one is controlling them, but they are programmed to collectively build a specific design. Imagine the applications: swarming robots building levee walls along a dangerously flooded coastline, thousands of tiny robots constructing a space station on Mars, or deep underwater gas pipelines being assembled by swimming swarms of bots. A similar experiment used a swarm of autonomous flying robots to build an artfully undulating brick tower. 3D printed houses. 3D printing has finally gone mainstream. MakerBot is selling nifty, and just about affordable, desktop machines that can print out fully rendered 3D plastic toys, jewelry, machine parts and artificial limbs. But what if you want to print something bigger than a shoebox? Could you actually build a 3D printer large enough to print out a plastic house? The answer is yes. A Dutch architecture firm has launched an ambitious public art project to build a 3D printed house. But first, they had to build one of the world's largest 3D printers, called the Camera Maker or Room Maker. Using the same plastic source material as small-scale 3D printers, the Camera Maker can print out large Lego-like plastic components that will be assembled into individual rooms of the house. The rooms will then lock together, again, think Lego, with the printed exteriors of the home designed to look like a traditional Dutch canal house. Meanwhile, a Chinese construction company is building houses using a giant 3D printer that sprays layers of cement and construction waste to assemble the homes. The company says the houses will cost less than $5,000 each, and it can produce up to 10 of them in a day. Smart roads. Google is hogging all of the limelight with its self-driving car. But what good are smart cars if they still have to drive on dumb roads? One of the most exciting new ideas is a roadway that acts as a charger for electric vehicles. A New Zealand company has already built a large power pad that can wirelessly charge a parked electric car. The next step is to embed the wireless charging technology into actual road surfacing so electric vehicles can recharge on the move. No more refueling stations. Other intriguing ideas that may come true one day include road surfaces that absorb sunlight to generate electricity, or, even cooler, embedding the road with piezoelectric crystals that capture the vibrations of passing cars and convert them into usable energy. Building with CO2. Carbon dioxide spewed from power plants and automobiles is the single largest source of man-made greenhouse gas. Every year, we pump more than 30 billion metric tons of CO2 into the atmosphere where it speeds the damaging effects of global warming. While the energy sector experiments with trapping or sequestering CO2 emissions underground, a team of researchers at Massachusetts Institute of Technology has successfully used genetically modified yeast to convert CO2 gas into solid, carbon-based building materials. Like the Harvard termite team, the MIT researchers were also inspired by nature. This time the abalone, like other crustaceans, abalone can convert ocean-borne CO2 and minerals into calcium carbonate to build their rock-hard shells. The researchers isolated the enzyme that abalone used to mineralize the CO2 and engineered a batch of yeast to produce it. A beaker full of genetically modified yeast can produce 1 kilogram of solid carbonate from only 0.5 kilograms of CO2. Imagine how many carbon bricks they could make with 30 billion metric tons of CO2.